All right, the next section, the next four sections again, they'll all be inverses of each other. They're going to be all related. And once we start seeing the connection, it'll flow from there much easier. The first thing we're talking about is exponential functions. Up until now, we have had this f of x equals x to the third, some x to some power. We've had x to some power. Now we switch it. Exponential functions are like this. Notice the x was the base here, but now the variable is the exponent. These are called exponential functions. As long as a is greater than 0, it's positive, and a does not equal 1. Because if it equaled 1, then we have nothing to worry about. So a is the base. And it could be any number, any fraction or any number. It just has to be greater than 0, has to be positive, and it cannot equal 1. In other words, it can go from 0, or a, or a can be greater than 1. So I go from 0 to 1, and then greater than 1. The shape of the graph, the direction of the graph changes when that occurs. So here are some examples of what I mean by exponentials. So again, the base can be any number other than, cannot be 0. It has to be greater than 0, and it cannot equal 1. So for example, that's an example. That's an example. As long as the exponent is the variable x, that's what we're looking for. What do we know? By if let's say for this example, a is 2. X can be anything. The domain of x is negative infinity to positive infinity. What do we know about x? What do we know about this function? 1, f of x will always be greater than 0. It'll never be negative. It's increasing if the base is greater than 1. If it's decreasing if the base is fraction. So we have, let's look at 2x. What happens when x if x is a fraction? Let's say if x is negative. So we have 2 to the power negative 3, which becomes 1 over 2 to the power 3, which becomes 1/8. If x is negative 2, 2 to the power negative 2 is 1 over 2 squared, which is 1/4. If it's -1, so it's 1/2, which is 1/2. You notice it's getting bigger because the bottom number is getting smaller. When x is 0, anything to the 0 power is always 1. When x is 1, when x is 2, so when the x values are negative, they're very small. The bigger the negative number, the smaller the number. When x is positive, the bigger it is, the bigger. So the graph of the function, the graph of when a is greater than 1 will always look like this. And always crosses the y-axis at 1. It has a horizontal asymptote. It never crosses the x-axis, and there is no x-intercept. And it keeps on going as long as x gets going. So this is when x is positive. All right. So let's see what happens when the base is a fraction. When a is between 0 and 1. In other words, fraction. Let's say 1/2. So let's look at the graph of this one. 1/2 to the power of x. We'll do the same things here. So we have -3, -2, -1, 0, 1, 2, 3. And then we'll draw the graph. So what we have here is 1/2 to the power -3. Negative exponent simply means flip that. So it means 2 and drop the negative, which makes it 8. So at -3, it's 8. It's all the way up here. 5, 6, 7, 8. When x is -2, 1/2 to the power -2. Negative switches. So we flip 2 squared is 4. When x is -1. So the negative sign means I flip the inside and equals 2. At 0, anything to the 0 power is 1. So at 1, it's 1/2. So distribute, so it's 1/4. So 1 cubed is 1, 2 cubed is 8, so it's 1/8. So this graph is a decreasing graph. Oops, damn it. Oh, I missed it. Sorry about it. So it looks like that. So if a is a fraction, it's a decreasing graph. As x goes to infinity, the graph goes lower and lower and lower and lower. Yeah, so that was pretty much example 2. The example 2. Now, so example 3, it says graph each of the following of the function 2x. So A is f of x equals 2x minus 2. F of x equals 2x minus 4. F of x equals 5 minus 0.5x. These are all just transformations. So let's look at this first function. First, we know the function is 2 to the power x. That looks like that. It crosses that 1. Now what this says, we have a horizontal shift because it affects the x directly. Horizontal shift. So set the x minus 2 equals 0. Our new x is 2. So there's my new vertical axis. So at 1, it crosses there now. Just everything, the whole graph just shifts over 2 spaces. That's what that means. Here's 2x. This is outside of it, so this is a vertical shift. Our original function is 2x, and that looks like this. There's no horizontal shift. Since it's outside the function, then we have a vertical shift down 4 spaces. So what this one says, remember our graph used to look this has, so now I move this 1, 2, 3, 4. So there's my new horizontal line, the x-axis. The y-intercept still happens 1 above there. So there's a graph. It just shifted down 4 spaces. Five minus 0.5x. All right. So the original function here is 0.5x. 0.5 is the same thing as 1/2. A is now between 0 and 1. So that means our graph looks like that. It's a decreasing graph. There's no horizontal shift because there's nothing on the x. There is a flip. A horizontal rotation. Because what we have now is a negative 0.5x. Ooh, no. This is a vertical because it's outside the function. If it was negative, it would flip this way. But since it's outside the x, it's a vertical. So now instead of crossing at 1, it now crosses at -1. It shifts across the entire x-axis. So there's no horizontal shift. There is a vertical shift. It's a flip because it's outside the function. And 3, since this is outside the function, this is the vertical shift. It goes positive 5. It goes up 5 spaces. So there's the old. So let's go up 5. 1, 2, 3, 4, 5. There's the new x-axis. My intercept is 1 below there. So my new graph looks like this. So we do the same as we did earlier with our functions, our transformations. Exponential functions are used a lot in the real world. Mostly we use them in finance. But something, whenever you borrow money or you buy a car or buy a house or something, you have to pay interest. There's simple interest, which is the amount you pay back, is based on, it's called an annuity. The principal, the amount you borrowed, how long you borrow it, and what rate you borrow it. It's just a one-time thing. But more so, they use something called compound interest. This one now, because the difference between the simple interest, because this is you borrow money for however long you borrow it, it's just one set fee. Compound interest is each period, whether it's weekly, monthly, annually, or whatever, it recalculates the interest and adds it back to what you owe. So that's why you owe a lot more. If you buy a car for $30,000 and finance it for 5 years, you could end up paying $42,000 for it or $45,000 for it. So the annuity, the amount you pay back, is this formula, where A is the annuity, the amount owed, P is the principal, the amount borrowed or financed, N is number of payments, and T is time in years. Typically, they're in years. So if you pay something quarterly, that's once every quarter. There are 3 quarters in a year. Their quarters are cut down in 4 pieces. So we have 3 quarters, 3 payments in 5 years. So you're gonna make 15 different payments. So this is why it adds up pretty quick. Let's see if there's an example here. Yeah, okay. Here's example 4. Put it up there for you. Suppose that you borrowed $1,000 or you invested $100,000 at 6% interest, compounded semi-annually. So that's n equals 2. It happens twice a year. Find a function for the amount in which the investment grows after t years. So leave t alone. So we have here, our p is $100,000. Our rate is 6.5%, which makes it 0.065. It has to be in decimals. And n is 2 since it's semi-annually. It happens twice a year. And then t we're given here is 0, 4, 8, 10. So that's 0. So whenever you convert from a percent to a decimal, just move it 2 to the left. So 6.5%, drop this and move it 2 to the left is 0.065. N is 2 and T is 0, 4, 8, 10. So how much you'll pay back is with this formula, 100,000. 1 plus the rate is 0.065 over 2 and 2 times t. So the first time you put 2 times 0, so it's 0. So if at 0, even before the first week, you only owe $100,000. Because 2 times 0 is 0. Anything to the 0 power is 1. And 1 times 100,000, 100,000. So at t equals 0, the annuity is $100,000. At t equals 4, the annuity is 1 plus 0.065 over 2, 2 times 4. Actually, we can make it even simpler. So it's 2 plus 0.065 over 2 over 8. So it's 2.065 over 2 over to the power 8. Type in your calculator, do this first, 2.65 divided by 8. Look for your key that looks like this. Press that, enter 8. Then times 100,000. You'll get your answer. You do that for all of those. All right. So this is how we use the compound interest formula, which is interesting because in 1741, just as all this, we had Leibniz or Newton or Leibniz, I forget which one of these two, came up when they were in the process of discovering calculus. They came up with the number E. E is a constant. What happens is if you took this annuity formula R over N and T. So as N goes to infinity, eventually this goes very small, and this keep on going, going, going. So this gets very large. So 1 to the very large times your principal. So what happens here is this, is if you took $1 and invested it, if you took $1 and the interest rate was 100%, for 1 year. And as that goes, so what we have here is this. 1 times 1 plus 100% in decimal is 1. 1 over n. N times 1 is n. So what we have is 1 plus 1 over n. So as n goes towards infinity, first off, n starts at 1. Then n goes to 2. Then n goes to 3. N goes to 4. When n is 1, 1 over 1 is 1, 2. So a is 2 when n is 1. When n is 2, we get 1 plus 1/2 to the power 2. So it's 3/2 to the power 2, which is 9/4, which is 2.14 or 2.25. When n is 3, this is when n equals 1, n equals 2, n equals 3. So we have 1 plus 1 over 3 to the power 3. 1 over 3 is 0.3333 to the power 3 is 2.41 something. You keep on going this, and this number will eventually slow down. And it gets very close to this number. And it goes on forever. If we graph it, because the larger n gets, because this gets smaller, the 1 over n gets smaller, and this increase gets smaller to the power, and eventually we end up, we plateau at this value here. And that number is that. And that's what we call E. Euler, that's his name. In 1749, I think, so in 1700s, he came up with this theory. And this number was named after him. That's why they call it E. This is called Euler's number. And we'll see a lot of this. You'll see a lot of this in upper math courses, and if you take higher level business courses and stuff like that. So let's look at example 5. What is E cubed? What is E to the negative 0.23? And what is E to the 0? Anything to the 0 is 1. That's an easy one. So with this one, you go in your calculator, type in E, you'll see a button that says that. Click it and just hit enter 3, and it'll give you the answer. And you for n, you can put negative 0.23 and keep on going from there. So that's what's happening there. Again, now the graph of it looks the same because this is an exponential function. And it crosses that 1. This is the function of e, e to the power x. We just use n for our counter from the last example of the compound interest. So All right, so that's what E is all about. And again, E is a button on your calculator that you can just plug it in there. Okay, that does it for that section. That does it for section 2.